Okay. So it says 3 seconds after being released. 3 seconds after being released from rest. So everybody, the boxes. So notice we've got 1, 2, 3 boxes, and then a mouse is on that bottom box, and it's connected to the upper box with a Twizzler. In other words, instead of being boring and AP just cutting the string, we're going to have the mouse eat through the Twizzler. Okay. And after some additional time has passed, the system begins moving in the opposite direction. Now, they haven't really told us the original direction of motion, but hold on, we'll figure it out. Is the new motion greater than, less than, or equal to 3 seconds? Okay. And so let's talk about, we release it from rest. What direction is it going to go? And if you take that forward is positive approach, well, the left side has a total of 3 kilograms. What about the right side? It has a total mass of, looks like 3 if you're not careful, but don't forget the mouse is there. So it'd be 4 kilograms. And so what direction is this system going to go? The mouse is going to go what direction is the mouse going to go? Not in free fall. We haven't eaten through yet. We're just released from rest, right? So if you have 4 kilograms here on the right, 4 is greater than 3. And so 4 is going to determine the direction of our motion. And so down on the right is going to be positive. And at that same instance, what's the 3 kilogram on the left going to do? It's going to move up. So up is forward on the left, okay? And so remember, a pulley changes the direction of motion. Be careful. It's not just up is positive, down is negative anymore, okay? Forward is positive, should work for you. And so 3 seconds after being released from rest is when the mouse eats through the Twizzler. But what about in that 0 to 3 seconds? We're accelerating, right? So let's solve for the acceleration from 0 to 3 seconds. Well, to do that, step 1 is what? Got to do a diagram, okay? And so let's draw a diagram. Now, it could get real detailed. We have 4 objects here. But in the first 3 seconds with that Twizzler intact, isn't it like it's just a right side system? Okay, so we'll draw a diagram for the right side system. I'm just going to draw you a different one. Okay, hopefully that one works. And so I'm going to look at it in the first 3 seconds before it eats through the Twizzler as a 3 kilogram on the left and a 4 kilogram on the right. Good there? And so 0 to 3 seconds, I would have our 3 kilogram. We've got a gravitational force. I'm going to say FG3. And then it's going to accelerate in the upward direction, we said. And so it's connected to a string. So tension is going up. How big do I draw it? Is it equal to the weight, smaller than the weight, or bigger than the weight? If we're accelerating upwards, it should be bigger. And so I want to make sure FT is bigger than FG3. That way you have an unbalanced force in the upward direction. Good on the 3 kilogram? And then the rope, remember, goes over that pivot point. That's all the pulley is to us right now. We don't care about any rotation of the pulley. And so on the other side, we have FG4, which is going to be a little bit bigger, right? I'm going to make it a little bit bigger. I don't want to equal to the tension. FG4. And I don't want to equal to the tension. It should be bigger than the tension if you want to accelerate in the downward direction on the right side, yes? And so FG4 is bigger than the tension. Now the two tensions we have here, hopefully you remember last class, I said without considering any rotation of the pulley, these two tensions are equal and opposite. Oh, let me call it FT. FT, there we go. These two tensions are equal in magnitude. Are they opposite in direction? They're both up. So at first glance, you're like, no, they're the same direction. But remember, forward is your positive direction. This tension on the left-hand side is positive, but the tension on the right-hand side is not in the direction of forward motion, it's backward. So it's negative. And so these two tensions are equal in magnitude, opposite in direction. And notice they're on two different objects. What can we identify with these two tensions? They are equal and opposite on a pair of objects. So they are representing Newton's third law. And it's important to recognize that because here in a second, when we write a FNet individual statement, and then we end with a FNet system, your internal to the system forces should cancel out. Okay. Which is the next step, FNet statements. We've got our diagram, we've got our positive direction, and so now we can do our FNet statements. And so FNet for the 3 kilogram is going to be forward minus backward, if you will. And so I've got a positive tension minus FG3. And then same-ish for the 4, FNet for the 4 kilogram. And again, we're looking at the right side as a collective, And so FG4 is our positive force, and then our minus FT. So left side, right side, FNet statement. Then if we put them together to make a system FNet statement, there's a couple ways we could approach this. You can say FNet system, or I don't know what I did last time, but you can say FNet 3 plus FNet 4. It's the same thing as saying FNet system. And notice positive tension, negative tension. What happens to those internal to the system forces? Positive value, negative value. It cancels out. It doesn't zero out. Tension is not zero. Otherwise, the string would be cut and no one would be moving, at least not as a system. They'd both be in free fall. And so tension cancels out, and what remains? Now, if you look too close, if you don't use subscripts, you're going to have FG minus FG, and you'll be like, well, FG cancels out. Well, that's incorrect. FG4 is bigger than FG3. And so it'd be FG4 minus FG3. And we can take both of those and break them down. Say it with me. Everybody get corny with me. FNet equals MA. Which mass? It's a system. And the acceleration is this forward acceleration. So I can't say it's up or down. It depends on what side I'm talking about, right? But it's that forward acceleration. And then FG equals, what can I plug in there? mg. Now be careful, it's m4g minus m3g. And if you want, you could factor out g or leave it. It's not hard, right? It's 10. And to get this acceleration of the system, at least initially, before the Twizzler's gone, then I would have 4 times 10 minus 3 times 10, all divided by, you got to solve for acceleration, you got to divide by the system mass. And yes, I know we all know what 4 plus 3 is, but I'm going to go on and show it. And so we get 40 minus 30, which is 10 divided by 7. So 1 and 3/7, someone work it out. It's 1 point. What would we get? A little less than 0.5, 1.4 what? I just can't hear that. 43 and meters per second squared. It's in the forward direction, right? Forward direction. Everybody good? And so now we know it accelerates 1.43 meters per second squared in a time frame of 3 seconds. They started from rest. Couldn't we do some kinematics and figure out how far they travel or such? Maybe we need to, maybe we don't, but we could. We now know that. Well, then the string is cut. I mean, then the mouse eats through the Twizzler, right? After some additional time has passed, the system begins moving in the opposite direction. Now, what does that mean after some additional time has passed? So I wish I had an animation of this, but if they move together, up on the left, down on the right, and then all of a sudden, the mouse chews through the Twizzler, so mouse just drops to the floor, we'll assume safe, right? Also drops to the floor that 1 kilogram on the bottom. And so after you cut through the string, what would it look like? Or the Twizzler, sorry. After the chew, we have a new picture. What would it look like after the chew? Well, we still have 3 kilograms here on the left. What do we have over here on the right? A total of 2. Now, at that moment, so this is after 3 seconds, right? Remember, it was moving down on the right. Original motion was down on the right, up on the left. Well, now look at the difference in mass. Now, who's going to try to win? If this is where we started, would we say it moves down on the right? No, 3 is bigger than 2. And so now it has to slow down in that forward direction. And what's eventually going to happen as some time passes? It's going to start going the other way because 3 wants to win. And so the new motion would be up on the right and down on. But in between that change, what has to happen? A split second, stop, right? And so between these, you have to have a stop momentarily. Good deal? Okay, so it has to stop moving in the original direction, and then it'll begin moving in the new direction. Okay? Will we have exactly the same acceleration? What will the new acceleration be? Let's figure it out. And so the new motion, so I'm going to switch to blue, we would have what diagram? We'd have FG3 down on the left, and then we'd have a tension force pulling up. With the new motion, what's our positive direction? down on the left. So FG3 would now be positive and FT would be negative. And then our 2 kilogram would have a smaller FG2, same tension, now not same magnitude, okay? If you were to solve for each of these tensions, they're gonna be different values, but it's still gonna be a Newton's third law pair. It's still gonna be equal and opposite to the tension on the other side. And it's gonna be up on the right. Well, that's our new positive direction, okay? And so we've got our diagrams. Let's do our FNet statements. And so again, this is all after the chew. And so FNet on the 3 would now read FG3 minus FT. Do y'all miss your elementary days? The age of innocence, it's gone. Anyway, what about FG2? Now it would be tension minus FG2. And to find the acceleration of the system, remember each object is going to accelerate the same amount, same as a system. We came to that conclusion last time, right? Put them together and we should see whatever tension is now, different number, but it's still equal and opposite. So it still cancels out from a system approach. And then what's left? We got FNet of the system equals FG3 minus FG2. And so mass of system, FNet equals what? MA, so mass of system times the acceleration of the system would equal M3G minus M2G. And to solve for that acceleration, it would be, again, you can factor out the G or not. So it's the difference in the weights divided by system mass. Now, before I plug numbers in, it's kind of what we did originally, right? We had M4G minus M3G. We're still going to have a difference on the numerator of 1 times 10. Yes? So does that mean we get the same acceleration? Well, how does the denominator change? And so we still have 3 times 10 minus 2 times 10. So we still get 10 on the top. But the denominator is no longer 7. With the mouse and that bottom block gone from the system, what's our system mass? 5. And so our new acceleration would be what? 2 meters per second in the new forward direction. Does that make sense? So we've got a greater acceleration. So here's your full picture. Go back to the full system and they accelerate one direction. And then it chews through the Twizzler. It leaves the system, the mouse in that bottom block, but it has to come to a stop and then speed up the other way even more. Yes? Yes, yes? And so what are they asking us to find here? Is the new motion greater than, less than, or equal to 3 seconds? And so 3 seconds is that time before the chew. Let's find time after the chew. And so first, we actually need to solve for that final velocity of segment 1, of situation 1, because it's going to be the initial velocity of our second scenario. Yes? And again, AP is not probably going to have mouse and Twizzler, okay? They don't tend to use animals in there. I mean, maybe, but they're not going to let a mouse drop to the floor, right? Okay. So they'll probably just say the string is cut. And so let's do a little kinematics. Let me switch back to purple. Kinematics of segment 1 before the chew. And so we know it started from rest. We know the original acceleration. And they said that 0 to 3 seconds was before the chew. So can we find the final velocity, which later will become the initial velocity after the chew? So that's why we're doing the initial part first. What equation are we going to use? Which kinematics equation are we going to use? The first one. We don't know distance, and we're comparing time, so we don't need the distance piece. And so VF equals V initial plus AT. And so VF is what we're looking for. VI zeroes out. And so 1.43 times 3 seconds would be what? .29, so about 4.3 meters per second. Okay. Then we need to know the timing, actually. I'm running into a mental issue there, though, because we don't know where it's going to return to. Is the new motion greater than, less than, or equal to 3 seconds? Maybe they just wanted us to solve and compare the accelerations. Because here's why. Here's where my mental block is coming. If we do kinematics now, after the chew, what do we know? We know now the initial velocity is 4.3 meters per second in the old direction. So we're going to have to make a change at some point. We know the new acceleration is 2 in the new direction. So it depends on what you want to call positive and negative. I got to make somebody negative though, right? Can't do kinematics with opposite directions. Are y'all okay if I just go -2? The new direction is opposite the original direction. So I'm going to say -2. And then what else do we know? You can't find time of the new without a distance or a final velocity. So maybe, let me check the key. I think maybe we're just comparing the accelerations. Okay, so hold on one sec. There's not enough information. So close. Where is it? There it is. So yeah, before the chew, 1.4, after the chew, 2. And so, yeah, that's all they solved for, was the accelerations. So it originally sounded like we wanted to compare the times, but we don't know enough. We'd have to actually be given a time frame or a distance or final velocity. It's not going to come to a stop though and stay at a stop. Yes? With a higher acceleration, okay, if all we considered was, well, when does it bring it to a stop? You got a higher acceleration, you're basically reversing the change in velocity. And so we can do that though. Let's do that. Using the same equation, VF minus V or equals VI plus AT. So it started from rest before the chew. We're going to come to a rest, 4.3. And we know the new acceleration. We can find the time for it to reverse to a stop. Do that. And so 0 minus 4.3 divided by the new acceleration. How much time would it take to bring it to a stop? More time, less time? .1 something, and you would compare that to 3 with the original acceleration, right? So if you just reverse it, how long does it take to come to a stop before speeding up the other way? It would take less time. you've got a higher acceleration. Does that make sense? But then it's just going to keep going in the new direction, right? Until, I guess, one block hits the floor. Moral of the story, when you cut a rope, not only are you missing pieces of your system, right? But your system mass changes, your acceleration of the system changes, okay? And so it's basically a new problem. Questions on the side-by-side. Force diagram. Define your positive direction. I like forward to be positive. And then FNet statement solve. Yes, question. So it was just because I was using the initial, you're talking about right here and right here. Okay, so when we did kinematics, the mouse or the right side was moving downward, and we had said that was positive. And so when you solve for final velocity, I got a positive in the old direction. But after the Twizzlers chewed through, that's the initial velocity. And so I had it as a positive here, right? With the old direction, but I can't make the new acceleration positive and combine it with the old direction positive. You gotta, for them to be in the same equation, you have to be consistent with your sign. And so if initial velocity is old forward positive, then your acceleration after the chew would be in the upward direction. And so I made that one negative. It just has to be consistent, or else we would, if we solve for the time, you'd get a negative time, and that should be a red flag. Good deal? Any better? Okay. Well, let's try a different kind of pulley problem. Let's go to, I gotta find it. I think it's back on page 18, yes. So we did the top, that was a side-by-side. Atwood machine is officially what it's called. Down below, I call it a tabletop pulley, or it's called a modified, by the way, Atwood. That's its official name. And all it does, one of your blocks, instead of hanging, it's on a tabletop. Now, maybe that table has no friction. That would be easy, right? If it's a frictionless table. But this one, we're going to have friction because there's two parts to this one. Initially, we're going to find the maximum amount of mass that can hang off the side. Notice they don't tell us, they just say MH. We're going to find the maximum mass that can keep that block on the tabletop stationary. And so again, just a refresher on that friction. The static portion of this graph has a maximum. And that's what we're going to be using to find that unknown hanging mass. And then we're going to change it. We're going to add more mass, and you don't know that it's more yet, but it should be more because we want the thing to accelerate, okay, as a system. By the way, if you're stationary, what's the acceleration of your system? 0, right? And so that's what we're going to do here. There's no reversal of direction. What would it take to reverse the direction? I guess somebody would have to pull on that tabletop mass, right? And override the weight of whatever's hanging, okay? Okay, stationary to start. Step 1 to any force problem is what? Diagram. And so we've got 2 objects, we've got 2 diagrams. Now, yes, one is on a tabletop, so that kind of goes back to our previous like norm, if you will, not normal, but norm, our everyday type problems. And then the other one is going to be only in the vertical, but just let forward be your direction, okay? And so tabletop, maybe I draw it over here. So our 6 kilogram block, I'm putting it kind of at an angle to the dot because hopefully you see we're going to have some right and down forces on the 6 kilogram. So what's our down force? Oh my, what's the down force on the 6 kilogram? And everybody says gravity. So FG6 if you want. Again, if you want to relabel these as block 1, block 2, block A, block B, you can do that. What other forces are acting on the 6 kilogram block on the table? There's a normal force. And so what direction will the normal force go? Straight up, perpendicular to the surface. And how big do I draw it? It's stationary, the same. So we want it to balance. And so equal and opposite, Newton's first law. When you play the balance game, it's first law, okay? Newton's first law about balanced forces. What other forces are acting on the 6? We've got tension. What direction is this string trying to pull? Or it is pulling, but it's trying to pull. It's to the right, okay? And so I'm going to draw FT to the right, not necessarily equal to the vertical forces. Okay, so I'm not going to put a tick mark on that one. What other forces are acting on the tabletop mass? Right, if this thing is not moving, there has to be something to oppose that tension force. So I could put 2 tick marks on that one, right? These two are going to balance. And who's pulling it to the right? Who's gripping? I'm sorry, to the left? Who's gripping to the left? Static friction. Gripping friction. And that's it on the tabletop, right? It's gravity and whatever's touching. We got a string touching and a surface. But you got to remember, surfaces can have 2 forces. Perpendicular, friction is parallel. All right, what about the hanging mass? I got some room. I'm going to draw that one right here. What forces are acting on the hanging mass? We've got a gravitational force. Now we don't know the mass, so we don't know if it's bigger, same, or less than the 6 kilograms. And so I'm just going to, Goldilocks it. So FGH for hanging. Instead of mass hanging, it's a weight hanging, huh? What other forces are acting on the hanging mass? Tension. And if it's at rest, then I know that it has to balance. And so this tension force is going to balance. Now, careful, I've already got 1 and 2 tick marks. So maybe I do 1, 2, 3, 1, 2, 3. Balancing on one object, Newton's first law. Now we actually, before I write the FNet statements, hopefully you're in the habit of, ooh, this is a system. These 2 objects are going to pull on each other through a string. Now I haven't got nitty gritty with my labels, but can we identify the action-reaction pair, the Newton's third law pair? What forces would be the tension that they're pulling on each other? And so the tension that we just identified, it's going to be equal and opposite to the tension on the other side. And so it's a Newton third law. Ooh, hold on. It's a Newton third law pair. Okay. Are you noticing trends with Newton's first and third law? Okay. It's one force on each object. I push on you, you push on me, or pull, pull. And this is the force that should cancel out when we take a system approach, okay? All right, FNet statements. Now, we're not moving, but the would-be motion, and by the way, let's read ahead and be nice to our future self for consistency. Later, we're gonna have acceleration, okay? And so chances are, if we just let nature take its course, what direction is our hanging mass gonna go? The hanging mass would go, you think it's naturally going to go up? It's naturally going to go down. So what if we say down on the hanging mass is positive, that's forward. And what direction on the tabletop would be the same direction, same forward motion? As the hanging mass goes down, the tabletop mass goes to the right. So it's not because it's right. You could mirror image this picture, right? Or correct? But it's because it's forward. Everybody good there? And so I'm going to use this convention in my stationary. That way it also works later whenever I actually do accelerate. And so FNet statements, we're just going to care about the horizontal for the tabletop mass because the would-be motion is going to be in the horizontal. And so FNet for the 6 is going to be, I'm going to go with positive being first, so tension minus that friction. And then what about the hanging mass? So FNet H, the forward direction would be down, so I'm going to say FGH. And then tension is pulling the opposite direction. So with a system, put them together. Bless you. Bless you. Putting these two together gives us a system equation. So FNet system. Notice what happens to your tension. It doesn't zero out. It is something. But I've got positive and negative. Your Newton third law pairs are internal to the system. They should cancel out when you take a system approach. And what remains? We've got the weight of the hanging mass. Now with our side-by-side, it was minus the weight of the other object, but notice the other side's on a table. The other force would be the frictional static force. Everybody good there? FNet equals MA, which mass? It's a system. Now one is unknown, that's okay, just hold tight. Equals FG equals mg, and there's that unknown mass that we're going to be looking for, minus, what's our newish, what's our last week equation for force of static friction? It's the coefficient of static friction times the normal force of which block? Well, there's only one block that has a normal force. It's for the 6. What can we plug in there? Right, we said the Fn was balancing the weight of the 6 block. And so we can plug in m of the 6 times g. And so mhg, oh, not equals, sorry, minus, equals, and then I'm going to spend some time with the system mass. It'll be m6 plus mh. So there we are. That's broken down into simplest terms before numbers. All right, so what are we looking for? We're trying to solve for MH. Well, it's in 2 places, right? Now that's possible, but there is a simplistic part of this problem. In part one, nobody's moving. And so what's our system acceleration? If nobody's moving, 0. So our acceleration on the left zeroes out, which means what about mg and mu mg? Different masses, but they're going to equal each other. And yeah, careful. Masses don't cancel, but oh, g's on both sides. What happens if you've got g on both sides? Yes, you can. Cancel. And you're like, but I know it. Okay, multiply with it. It's okay. We're trying to solve for that mh. And so, and by the way, it doesn't really say this, but this is a maximum hanging mass since we're using a maximum static friction, okay? And so if we were less than the maximum, that's okay. It'll still be at rest. But this is the maximum limit of that static friction. It's that peak of the graph, right? So we are solving for that maximum static friction, and we're finding the maximum hanging mass that we can still have equilibrium. Okay. Well, we know the 6 kilogram, and then the coefficient of static friction, they said was 0.6. And so what's 0.6 times 6? 3.6. And so is the maximum hanging mass for that system to still be at rest. And that's what they asked us to solve for. There it is. What if I hung 3 kilograms? So if we hang 3 kilograms, what will the system do? It'll stay at rest. And how much actual friction would you have? Well, the actual static friction would be less than the maximum. And so remember the graph, you don't need maximum friction all the time. And if you're less than the max, it's a Newton's first law. You're just going to balance whatever is pulling on the box. Good deal? I draw that graph all year long. It's a good reminder. Static friction, not one number. Okay? When you calculate it, you're finding the maximum. What if I hung 4 kilograms? What if I hang 4 kilograms? What will the system do? It's going to go forwards. It moves forwards. And I like that word because the hanging mass will go forward down and the tabletop mass will go forward right. But it'll accelerate, right? Or correct? And so it'll no longer stay at rest. Okay, part B. Now watch this. We just said 4 kilograms will put it in motion. Technically 3.7 will put it in motion, right? If you want to get technical. Technically 3.61 would put it in motion, yes? And what are we going to do? We're going to put 70. That's much bigger than the 3.6 needed to keep it at rest. Much bigger. You hear that? What would the acceleration be? And so how does all this change? What about our diagrams? Do the diagrams change? There's one little thing, 2 things, 3 things. Yeah, let's draw new diagrams. Now we're accelerating, right? And so our new diagrams, basically they're going to not be tick marked. No more necessarily equal and opposite for everybody. And so new diagrams, your tabletop, now your vertical forces are still going to be balanced because it's not moving vertically. And so that's going to be true. Those are still equal. But now that it's accelerating forwards, which force has to be bigger? The tension is going to be bigger then your back force. And I'm no longer going to call it static friction. Now that we're moving, it's going to be labeled force of friction. Kinetic, yeah. Kinetic. So magnitudes change and the subscript on your friction changes. That's a change. You think AP would grade for those changes? Oh yeah, oh yeah. And then what about our hanging mass? Is it still going to be true that the tension force on each object is a Newton's third law pair? Would those still be equal and opposite? Yeah, they're still moving as a system. And so this tension, now earlier I had a triple, okay? Again, we'll have a new value of the tension, but they're still going to be equal to each other. And so I'm going to put 2s since we're on a new set of diagrams. But the hanging mass, 70, you don't have to be so extreme, but yeah, it's going to be extreme. 70 is much bigger than 3.6. And so FG 70. To find the acceleration, we got our FNet statements. They're going to feel familiar, but we're just not going to zero out acceleration. And so FNet for the 6, in the direction of motion, so still horizontal, it would be FT minus the kinetic friction. For the hanging block, it would be FNet, whether you put hanging or 70, now that we know a mass, either way is fine. It would be FG 70 minus that tension. And when you put them together to take a system approach, notice your tension, whatever it is, still a Newton's third law, it's still going to cancel out. And we'll have FG 70 minus the kinetic. FNet equals MA, which mass? System mass. System acceleration. And just a reminder, here, a system acceleration is the same acceleration of each block. And then FG equals mg. And I know the number. You're like, why don't you just plug in 70? Just be in some kind of habit, be ready for a variable form. Okay, AP loves variable form more than numbers. Numbers are a great way to just, oh, the answer's 2. That's a quick check, rather than the answer is mg minus mu mg divided by m plus m, right? It's an easier check. Force of kinetic friction is going to look the same as it did before, but instead of mu s, we're going to use mu k. But that normal force for the tabletop mass is still balancing the weight of the 6. And we're trying to solve for acceleration. So acceleration would be all of that top divided by, and I'm going to break down mass of system into mass 70 plus mass 6, MA plus MB, whatever. Does mass cancel? Mass 70s, numerator, denominator. Mass 6 is numerator, denominator, but they don't cancel. Why? Right, so on the top, there's a subtraction of the masses. If you were to factor out the G, right, and then mu is in there. And so the math is different on the numerator, denominator, so don't cancel, okay? And so, but now we're ready for numbers. So 70 kilograms is the mass, gravity's 10, minus mu k, I gotta scroll back up, 0.4, times 6 times 10, all over the sum of the mass, Again, I know you know it's 76, but I like to show the process. And so what do we got? 700 minus 60 times 0.4, is that 24? Over 76. So what do y'all get for the system acceleration? 8.9. Remember earlier I made a big emphasis about 70 being so much bigger than 3.6, right? We get a huge acceleration. And why am I saying huge? Hopefully you remember the other day I said when you put objects on a string and there's tension and it's a pulley scenario, your check is that your acceleration should be less than 9.8. Now technically that's true, but it's pretty close to 9.8, right? It's close to 9. So it's going to have a good acceleration, and you're not going to get bigger than 9.8 unless Superman or Thor comes along, right? Or Supergirl, Wonder Woman, whoever you want to pick, favorite superhero, okay, comes along and gives it a yank. That's a huge applied force compared to gravity, right? Assuming. And so it is less than 9.8, so we're good to go. Now, they don't tell us to, but I want us to get just a little bit of practice. Don't worry, it's easy at this point. Compare the tensions. The tension when it was at rest, the tension during acceleration. I've been saying they're a different number. Can we prove it? Let's find the tension when it was stationary and the tension when it's acceleration. Let's do acceleration first because we're right here. So to solve for the tension, I just have to use one of the equations. So which one do y'all want to use? The tabletop mass or the hanging mass? Because if Newton's third law is right, they should be the same. The horizontal one. So what if we find the tension using the horizontal, the 6 kilogram on the tabletop? And so I'm using that equation. And so I got to add friction to both sides. So doing a little algebra, the tension would be F net 6 plus the frictional kinetic force. F net equals MA. And then we've got that mu Fn, tabletop, mu mg. And so this is our new acceleration. So 6 times 8.9 plus mu k, we said was 0.4. And then 6 times 10. And so we know that number from before is 24. If only that was 9, right? 9 times 6. You get 52.4, 53. And so plus 24, we get 77.4 newtons. And so this is the tension in the string on both objects when accelerating, okay? Now, before we do the math, make a prediction. Is the tension in the string when everybody was at rest, should it be equal to 77? Should it be less than 77, greater than 77? Just make a personal prediction. And then we're going to go do the numbers and see. Everybody got a prediction? Okay, let's go up here, back to at rest. I'm going to go find those equations. And just for consistency, let's use the same 6-block tabletop block, but now we're at rest. We're back at rest. And so tension is going to still be F net plus, but now it's kinetic friction. F net equals, and everybody says, F net equals MA. However, when you're in stationary, you're at rest, what's your acceleration? 0. So we've got 0 plus mu k Fn, which is still going to balance the weight of the 6. Mu k was 0.6. Mass is 6. Gravity's 10. And so the tension is really just balancing the weight. We could have used the hanging weight, but what do we get? Not 3.6, we get 36. So when it's at rest, the tension is 36. When it was accelerating at that very large acceleration, it was 77. What if it was accelerating at 5? Tension would be somewhere in between. Hopefully that's what you were thinking, right? So tension is variable, just like normal force can be variable if you push up, push down, if you're on an elevator, if you're on a ramp. And so tension is variable, normal force is variable. Friction is dependent on the situation, right? It could be variable if it's static. Moral of the story, y'all, force diagram, F-net statement. If that's not your habit by next week, I'm gonna cry. I'm gonna cry. On the quiz last week or whenever it was, not a lot of diagrams, okay? The few that have come in to look at them for tutoring, what do I say? They say, I need help with number 5. I'm like, well, I don't see a diagram. Draw a diagram. Make that your habit for next week. Diagram F-net, diagram F-net, diagram F-net. Good? Because it's going to be your saving when you get a challenging problem. This is our last Pulley one. It looks like it's going to be our last one. So those other problems, pages I had planned, fingers crossed after the lab, we get them done. If not, I mean, I'll have them up next time. You can work on them during that independent practice time. So those will be, you know, guided practice type. And so this one, why did I say this one's going to be a challenge? Look at the picture. What do you see? It's at an angle, so we got a ramp. There's that thing on the end of it, so it's also a pulley problem. And then when you start reading, it's got friction. All 3 big ideas together in one, okay? This isn't an easy one. It's one where you got to go slow, pay attention to detail, and watch your subscripts. Because we got a system. We got 2 objects here. The following has a coefficient of kinetic friction. At least we know the system is what? Moving. We don't have to make that decision, right? If they gave you both, maybe you'd have to calculate the maximum static to see if it would even move in the first place. But we are moving 20 kilogram block and a 75-degree incline. The coefficient is 0.2. So I know the wording was weird there a little bit, but our kinetic coefficient is 0.2. Now they don't specify in the picture where 75 degrees is. And you can kind of base it on the picture. Most times, unless told otherwise, your ramp angle is with the horizontal at the bottom. So we're going to make that angle at the bottom 75 degrees. Good deal? Good practice. Step 1, free body diagram. And it even says no components. It's just reminding you that on the AP exam, they do not want to see components. I'm going to draw them, of course. It's going to be my chicken scratch. So if this was the real AP exam, give them what they want, chicken scratch in the margin, okay? And then step 2, write your F-net statements. Now it says X, Y. There's a ramp here. I like the parallel perpendicular. If you want to call it X, Y, that's fine. And then what's the acceleration? And I doubt we have time, but you can even do E. What's the tension? Okay, so you've seen it cancel out when we solve for acceleration, but once you know the acceleration, you can plug it back in. You could even say, oh, what if all this is at rest? Determine the maximum coefficient of static friction. You could even turn it to what would it need to be in order for this to be at rest? Hint, hint, that's what we're doing in lab, I think. It's one of the things we talked about. What is the static coefficient for the system to be at rest? Okay, so you could even do that. Okay, force diagram, we got two. I'm going to try and keep with maybe left side, right side. And so our 20 kilogram block, let's put it right there. So what forces are acting on the 20 kilogram block? Call it a tabletop, it's on a ramp, there's a surface, so don't forget that. What do we got? Our every time force better be what? Gravity. Now look at your masses in the picture, 20 kilogram, and then do a little squinting, 180 kilogram. And so, you know, I'm not going to do it super small. We got to do some things with gravitational force on a ramp, but I'm going to make it yay big. FG 20 or AB, whatever. What other forces are acting on the 20 kilogram block? Normal, it's going to go what? Up into the, tilt your head to the left. And so it's pretty sharp too, actually, right? And so FN, somewhere like that. What other forces are acting on it? Tension is going to be pulling it to the right, up the ramp, right? And so maybe it goes something like that. And then what? There's one more force. They mentioned coefficient of friction, so there's got to be a frictional force. And it says kinetic. Ooh, do we know what direction it's moving? Do they tell us? They don't directly tell us. And yes, it could, you know, the masses tomorrow may be a little different, make it harder to figure out. But with 180 kilograms hanging off the other end, what direction do we think it's gonna go? Kind of use a little gut instinct here. The 180 is gonna go down. And so we are making an assumption here. Don't worry, there'll be a tell. There'll be a way to figure out if we assume correctly. And so if 180 is heavy enough to go down, what direction is the forward direction on the 20? Up the ramp. And so we'll say, we're assuming up the ramp is going to be the direction of motion. Therefore, on our diagram, kinetic friction will act down the ramp. Okay. Now that would be the diagram to give AP. But I want to go on and draw the components. We're still in the learning phase. And so if you notice, tension, friction, parallel to the ramp. Normal, perpendicular to the ramp. Gravity is the only one that is not on our new XY axis. And so again, here's my procedure. Here's my steps. I start with FN and I draw my FG perpendicular because it's equal and opposite to my normal force. We're balancing Newton's first law. And then that's your new y-axis. I can identify the ramp angle in my gravity triangle. And so gravity's on old y, perpendicular's on the new y. And so that 75-degree angle is going to be there in my triangle. And then to complete the right triangle, FG parallel needs to be parallel to my new surface. And your check is FG should be what part of the right triangle? It should be the hypotenuse. And if your drawing doesn't show it as the hypotenuse, erase, make some adjustments, right? Okay, so there's the diagram. And I think that's one of the more intense diagrams we've done on a ramp, right? Okay. What about our hanging mass? What forces are acting on the hanging mass on the other side of the pulley? We've got gravity. Now, I am not going to measure out 9 times bigger, but isn't it going to be 9 times bigger, the weight, than our 20 kilogram, 180 and 20? And so I'm just going to, make sure it's bigger. FG 180. You could even do FGH for hanging. What other force is acting on the hanging mass? Tension is pulling up. How big do I draw tension? Equal to the tension on the other block. It's our internal force, right? And so FT, and I'm going to use my highlighter here, these two should be equal and opposite due to Newton's third law. So if you want to use a tick mark, I've already used 1 tick mark, so 2 maybe. By the way, no highlighter on the AP exam. So you would just write it out for yourself. Tension on block A equals the tension on block B, Newton's third law, okay? And that's it. And some of you are like, well, is it touching the side of the ramp? The intent is no. But if it did, there would just be another surface. There would be possible friction and normal force on that hanging block if it scraped the side of the ramp, right? But the intent is there's some spacing. It's not that intense. Not today. Good deal? There's your diagrams, y'all. You have to get the diagrams right because now we're going to write our FNet statements to solve the acceleration. And so I'm at the hanging block. That one's going to be easier. What's the FNet statement for the hanging block? Right. We said down was positive, so I'm going to have a positive FG 180 and then minus FT. And that's it for the hanging block. What about FNet for the 20 or the tabletop? Now we're just doing parallel. It's moving parallel to the surface. And so you just want to focus on the parallel forces. And so which force is pulling the 20 kilogram in the positive direction? I like to start with positive. Tension is pulling it up the ramp. Who's pulling it down the ramp? FG parallel and kinetic friction. Now, there's a couple ways to do it. You could use parentheses and say the sum of those 2 downward forces. I like to just keep them both. They're both pulling down the ramp. So I would say minus FG parallel minus that kinetic friction. If you show FG parallel plus friction, you need to use parentheses, okay? Because you're subtracting the sum. And then we're going to put them together. The acceleration is of the system. And so we got a lot here. So I need to leave a little extra space. And so FNet of the system is going to equal, and notice what happens to our Newton third law action-reaction pair, the tension. Whatever it is, it's equal and opposite. It's internal to the system. It cancels out. And so we would just have FG 180 minus FG parallel of the 20 minus the force of friction, kinetic, with the 20. So I added some more subscripts there just to differentiate, right? Block 1, block 2, block A, block B, whatever. Now, FNet equals, come on everybody, FNet equals MA. Mass of the system times that acceleration of the system, which is the same for everybody. FG for the hanging mass equals what? MG. And it's the 180 And you got to be careful. Now minus FG parallel of the 20, maybe you have this equation memorized. Maybe you look back at the triangle to figure out what trig function. What equation do we use for the parallel component of the gravitational force on a ramp? Sine theta. Parallel is opposite. And so it's going to be mg sine theta, which m, it's the 20. And if it was a frictionless ramp, maybe that's it. But this one's going to have friction. So minus mu Fn, but be careful, Fn on a ramp, let me go back to our diagram. Fn on a ramp equals Fn on a ramp equals the perpendicular. And which trig function do you use to find the perpendicular component? Cosine. So it would be the mg cosine theta. Again, if you want to memorize that equation, it's a 99% of the time. And so I'm going to plug that in. Don't forget your mu. Mu k times m, which m? 20. G cosine theta. Woof. All three involved is very involved. Real quick, we're almost out of time. Does math cancel out? If you don't use subscripts, you'll have M, and you'll cancel them out and you'll get it wrong. But no, they don't cancel out. Those are different masses. And so mass system is that mass 20 plus mass 80. Let's go on and do some numbers since we're almost out of time. And so 20 plus 180. Again, I know you know it's 200. I'm showing process. And then we have 180 times 10. And of course, OneNote is quitting on me. So write this down with me. If you're watching the video, follow along. So mass is 180 times 10 minus the mass of the 20 is 20 times 10 times sine, and our angle was 75. Minus the kinetic coefficient. I can't scroll, but I think it was 0.2, yes? Okay, so 0.2 times 20 times gravity 10 times cosine 75. I didn't see a lot of people writing. Your choice. And so when you solve for acceleration, somebody tell me what you get. 9.2? Oh, that is less than 9.8, isn't it? So let me go to the key and see. Ah, come on, hurry, hurry. I pledge allegiance to the flag of the United States of America, to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Honor the Texas flag.